Imagine opening a ledger of deep time and finding entire pages missing, as if someone folded back the margins and tore out a sequence of events that should explain how simple chemistry became thinking life. Picture a coastline where cliffs show normal layers of sediment and then a blank band that refuses to fit any known story. This is not a single cliff in a single town. It is a pattern traced across ancient shields and basins, from craggy plateaus in Africa to drill cores pulled from the floor of the Atlantic. If true, these prehistoric time gaps do not just rearrange chapters, they rewrite the grammar of planetary history. Today, we follow the traces left at the edges of absence, the scraps of mineral memory, the faint chemical phrases that survived whatever erased a chapter of Earth, to discover what those blanks might mean for origins, for cycles of reset, and for life itself. On this channel, we dig into anomalies that stretch the limits of geology and imagination, presenting evidence, expert debate, and the bold hypotheses that follow. Stay with us as we move from rock to lab to simulation and ask finally whether these gaps are natural scars or something resembling an intentional reset. But first, what does the rock actually show when you stand beside a cliff and feel the grain of time under your fingertips? The story begins at the interface between observation and absence, between field notes and the silence that those notes try to explain. Geologists name the phenomenon unconformity, but the unconformities that concern us are not mere erosional pauses. They are systematic voids in the stratigraphic ledger that do not obey local logic. You walk a transect and find sequences that should continue, but instead there is a discontinuity that recurs at equivalent stratigraphic levels across continents. At outcrop level, you see a sudden truncation of bedding, a polish in some places, and an inexplicable melt in others. Layers where the expected fossils of complex soft-bodied life are missing, while earlier and later records remain. In cores, the picture sharpens in ways that are at once more mundane and more troubling. Sedimentological logs show abrupt changes in grain size and mineralogy. Geochemical profiles reveal shifts in isotope ratios that do not match a single pulse event, and minute zircon crystals bear UP ages that bracket an interval of uncertainty far wider than measurement error. Studies from leading institutes report similar anomalies, papers in peer-reviewed journals describing stratigraphic gaps that line up when you place their chronologies against one another. Teams from university geology departments, national geological surveys, ocean drilling programs, and independent labs all contribute pieces of a larger mosaic. The mosaic suggests that something global and abrupt altered depositional patterns, or else a global process selectively removed or transformed evidence. Could glaciation stripped to bedrock explain all of it? No single conventional agent seems to fit every site and every data set. The gaps sit at the intersection of field observation and laboratory measurement, and they beckon for an explanation that must bridge timescales and disciplines. To understand the constraints, we need to step into the instruments. Radiometric data come from multiple systems, not only uranium-lead on zircon, but also samarium-neodymium, argon-argon, and rhenium-osmium where sulfide minerals endure. Each method carries assumptions about closed systems, parental isotopes, diffusion rates, and thermal histories. In several cores, scientists have documented discordant dates, layers that yield apparent ages inconsistent with surrounding material in the manner of a palimpsest. Crystalline inclusions show microstructural deformation, shock lamellae and minerals that look like the fingerprints of high stress. Trace element diagrams plotted against depth show windows of anomaly where rare earth element patterns shift abruptly, and sulfur isotopes move in ways that suggest changes in atmospheric oxidation state. Peer-reviewed studies from institutions that run high-precision mass spectrometers demonstrate that these shifts are not instrument noise or contamination. Deep-sea drill sites show sedimentary wipes where the stratigraphic signal is replaced by reworked material and horizons rich in exotic minerals that should not be present at those paleolatitudes. When paleomagnetic signatures are stitched together, some sequences indicate apparent polarity reversals or excursions clustered around the gaps, but not all. The pattern is messy. It resists a tidy single cause and therefore galvanizes multidisciplinary inquiry, from isotope geochemists and sedimentologists to computational planetary scientists. The evidence itself arrives in fragments that are concrete and amenable to protocols. Consider a core sample pulled from a continental margin, logged and described in a lab where the air smells faintly of solvent and machine oil. A technician slices a centimeter and polishes it for thin section. Under transmitted light, a microscopist notes a texture she cannot classify, a fabric of microcrystalline glass interleaved with rounded mineral clasts. A mass spectrometer returns isotopic ratios with decimals that refuse to fit the expected curve. A crystallographer finds lattice dislocations in zircons that are consistent with rapid heating and cooling. A team sequences organic biomarkers preserved in kerogen, molecules that bear signs of biological lineage but with enantiomeric ratios that puzzle chemists. These observations are combined with sedimentological context and then fed into models. Protocols for sampling include triple sterilization of coring equipment for organics, double-blind measurement of isotope standards, and cross-lab calibration using known cores from reference sites. A methodological description must include sample collection, cleaning, crushing, dissolution, and column separation, finally loaded into a thermal ionization or inductively coupled plasma mass spectrometer. Each step is described with precision so the result can be independently confirmed. This attention to protocol is why mainstream labs cannot be dismissed as careless when they report these anomalies. But data alone do not become a story until interpreted, and interpretation sits on the shoulders of theory. The conventional explanations begin with agents familiar to earth science. Extended glaciation can strip and erode, leaving gaps, while extreme volcanism can blanket landscapes in ash and reset biotic signatures. Large impacts can produce melt sheets and ejecta that homogenize records and create apparent discontinuities across wide areas. Mantle overturns and superplume events can reorganize deposition on a continental scale. Each of these hypotheses comes with testable predictions. For glaciation, we expect glacial till, striations, drop stones, and varved sediments aligned with isotopic cooling. For volcanism, we expect widespread tephra layers, volcanic gases trapped in mineral matrices, and chemostratigraphic indicators of acidification. For impacts, we expect shocked minerals, microspheres, iridium anomalies, and seismic signatures recorded in multiple basins. Field studies at several unconfirmation sites do show fragments of these signals in places, but not in the uniform pattern each mechanism would require. For example, some sites show shock metamorphism without corresponding global iridium anomalies. Others show tephra layers but not a consistent extinction of taxa. Voices from the scientific community argue cautiously, some defending multi-causal explanations where different mechanisms dominate in different regions, others pointing out that the temporal alignment of gaps argues for a synchronizing process. Interviews with experts convey this tension. Researchers with decades in the field offering reasoned skepticism, while younger modelers push for simulations that can incorporate complex planetary feedbacks. As the conventional theories strain to cover the full dataset, more radical hypotheses emerge that attempt to account for the scale and the selectivity of the gaps. One category of ideas frames the gaps as replacement events, periods when the biosphere was not merely perturbed but qualitatively reset. In such scenarios, the biosphere moves from one stable state to another through rapid restructuring, perhaps mediated by changes in ocean chemistry, nutrient cycles, or by a cascade of extinctions followed by a fast radiation from a narrow gene pool. Replacement hypotheses appeal to ecological dynamics, to tipping points, and to resilience theory. Another family of ideas points to panspermia-like mechanisms, where life is seeded or reseeded from outside, perhaps during intervals when planetary surfaces are more susceptible to sterilization and subsequent delivery of organic-rich material occurs. There are molecular fossil records that show strange discontinuities in biomarker composition, consistent with a turnover in metabolic pathways. Ghost fossils appear in the sediment record as impressions without the expected mineral replacements, ambiguous organisms that hint at life forms that might not fit our classification. Each of these radical ideas has philosophical implications, because if the record includes resets, then the narrative of linear progress is an artifact of survival, not of inevitability. These hypotheses are not wild conjectures without grounding. They use the available data to challenge assumptions and invite new lines of testing. Among the most intriguing physical archives are unusual crystals and mineral assemblages that behave as if they store information. In several cores and outcrops, researchers have found dense acervous layers of silica and complex aluminosilicates with structural anomalies that defy formation under standard sedimentary conditions. Some crystals contain trapped gas inclusions that, when analyzed, display isotopic ratios that do not match ambient ancient atmosphere models. In laboratory conditions, technicians can extract microinclusions and microchemical gradients that act as a form of temporal record. The notion of a crystal archive rests on the premise that under certain thermodynamic regimes, a mineral lattice can lock in compositional variations, like a slow writing process. Some scientists propose that high pressure fronts and rapid cooling can create glassy phases that record pulses of environmental parameters. Attempts to decode such archives involve scanning transmission electron microscopy, Raman spectroscopy, gas extraction lines, and isotopic mapping at micron scale. These methods reveal patterns that could be analogs of time series, sequences of anomalies embedded in a mineral context. The interpretation that some patterns are purposeful or designed is controversial and sits at the periphery of mainstream geology. Yet, the presence of impossible minerals demands explanation. Whether these minerals form through rare natural processes or through mechanisms that involve information storage, the existence of structured anomalies invites a detailed program of analysis and independent replication. Parallel to mineral archives, computational teams have reconstructed protocols that could generate the observed timings. Using general circulation models, coupled with mantle convection simulations and bolstered by astrodynamical inputs, modelers explore scenarios in which cycles of planetary perturbation align to produce synchronized gaps. For example, resonance phenomenon could amplify small orbital variations into climate swings that create windows of intense erosion or preservation bias. On longer scales, galactic motions and encounters with spiral arms might modulate cometary influx, leading to episodic bombardment that does not leave classic impact signatures but still alters surface chemistry enough to reset ecosystems. Some teams incorporate hypothetical quantum scale processes that would affect isotopic fractionation under conditions of extreme energy flux. Decoding these potential protocols requires high-resolution time-stepping, sensitivity analysis, and the careful treatment of chaotic behavior. Simulation outputs are then compared to proxy records, and where models predict a pulse of activity around a particular epoch, field teams test cores for matching anomalies. The collaboration between modelers and field scientists is slow and painstaking, but essential if we are to move from plausible mechanism to probable cause. The human dimension of these discoveries is immediate and visceral. Field researchers report a sense of dislocation when standing on an unconformity, a feeling as if history were not continuous but punctuated by human-sized blanks. Communities near key sites become small centers of attention, where local museums host debates and school children ask whether the past was different than teachers taught. Scientists themselves change as new possibilities arise, shifting research agendas, applying for grants to fund exotic analyses, and defending their hypotheses in journals and at conferences. There are also social tensions as radical interpretations leak into public discourse and are picked up by commentators who blur the line between speculation and conclusion. Policymakers ask whether such findings should alter resource management, cultural heritage protection, and disaster preparation, if the gaps hint at cyclical planetary instability. At a human level, the discovery forces a reckoning with narratives of progress and with the meaning of survival. Does the history of life include repeated near endings? And if so, what does that say about resilience and about our responsibility in a broader planetary story? To bring this story into sharper focus, we follow three protagonists whose lives intersect at the edge of the unknown. Dr. Elena Ruiz stands with a hand on a block of exposed banded iron formation, feeling its rough surface and smelling the damp mineral earth. Her backstory explains why she cares deeply about stratigraphy and why anomalies unsettle her more than most. Elena grew up watching tidal flats change with the seasons, and as a child she collected stones that seemed to hold stories. She studied geology in university and later trained in geochronology, learning to coax dates out of stubborn minerals. Her graduate years were marked by a slow disillusionment with neat narratives. She remembers a professor who loved tidy sequences as if history were an elegant novel, and Elena learned to listen for gaps. She spent a sabbatical in a lab where mass spectrometers hummed like nervous insects, measuring isotopes until patterns emerged that did not fit her early expectations. The intersection of fieldwork and lab precision shaped her style. She is meticulous about protocols and compassionate toward colleagues who must revise their theories. Elena carries the sensory memory of storms in coastal gullies, the taste of salt on her lips after a long day of mapping, the sting of cold winds that make your hands ache when you are thinly gloved. These memories anchor her investigations and also explain her stubborn commitment to follow anomalies wherever they lead. Marcus Hale learned to read maps by tracing fault lines with a pencil for hours, his fingers smudged with graphite and then with the soil of excavation sites. He arrived at the field of deep time through practical work in mining and then shifted toward academic research seeking to reconcile economic geology and paleoenvironments. Marcus has a distinct backstory of survival. He grew up in a town that experienced sudden subsidence due to groundwater extraction, and that childhood taught him about abrupt change. He chose to study sedimentary basins because he wanted to understand how environments can reorganize rapidly, sometimes with little warning. In his 20s, he worked on a drilling rig, the sound of winches and the taste of diesel embedded in his senses. And later in the lab, he learned to interpret sonic logs and core photographs. Marcus is a storyteller at heart. He narrates strata as if layers were scenes in a play. And that narrative impulse gives him an ability to synthesize field impressions into broader hypotheses. His backstory includes a mentor who taught him the art of cross-discipline collaboration, a geophysicist named Karen, and colleagues like Jonah and Priya who taught him the patient language of statistics. These personal connections are more than biography. They shape how Marcus frames questions, how he invites others into uncertain interpretations, and how he handles the political heat of controversial findings. Aisha Karoma arrives with a different set of senses. She listens to molecules the way some people listen to music. A biogeochemist by training, she grew up with mineral maps on the walls of her childhood school and with stories of rivers that once carried unusual sediments. Her backstory includes an apprenticeship in organic geochemistry, where she learned to coax signals from the noise of degraded organics. The lab she worked in smelled of solvents and coffee, and long nights hunched over gas chromatographers taught her the patience to read faint patterns. Aisha carries memory of a mentor who insisted that life leaves fingerprints in unexpected ways, and she believes that biomarkers can reveal episodes of systemic change more clearly than fossils can. She has spent years developing methods to detect chiral anomalies and odd-chain lipids in ancient kerogens, techniques that require absolute care in sampling and interpretation. Her sensory world includes the faint metallic tang of acid baths, the soft pink glow of lab ovens during ashing, and the tactile memory of pipettes and vials. These sensory recollections feed into a resilience in research. Aisha is comfortable with ambiguity and excels at turning ambiguous signals into testable hypotheses. Their professional interactions are populated by a cast of supporting characters who flesh out scenes and arguments. In field team meetings, there are names that recur, each bringing a facet of expertise and a personal style. Dr. Samuel Ito offers paleomagnetic insights with quiet precision. Fiona Marshall coordinates logistics and keeps the team grounded. There is Jonah Ellis, the sedimentologist, who laughs at grand theories but listens. Priya Singh, who runs simulation codes with almost religious devotion to verification. Karen Liu, who interprets seismics as if reading a living organism. Thomas Alvarez, the lab manager, who handles the mass spectrometers with the intimacy of someone who knows the instrument's temperament. And young field assistant Maya Brown, who asks the insistent questions that expose assumptions. At conferences, they are joined by visiting scholars like Abdel Ben Youssef and Helena Moretti, who challenge interpretations, and by policymakers such as Director Grant Alvarez of the National Geological Survey, who must consider the implications for resource mapping. These names represent nodes in a network of collaboration and tension, the human scaffold around data. Scene conversations unfold with expanded dialogue, gestures, and pauses to deepen the sense of human inquiry. At a campsite after a long day of mapping, Elena speaks with Marcus and Aisha, the fire warming their faces, the wind carrying the smell of crushed pine and diesel from the drilling rig. Elena says, "I do not like that blank. It sits wrong in the column." She pauses and rubs a finger along the rim of her mug, steam briefly fogging her glasses. Marcus replies, "It refuses to behave like a glacial unconformity, and it refuses to be a simple impact layer. The geometry just does not add up." He taps a notebook, where a sketch shows truncated bedding, his voice low, carrying fatigue and curiosity. Aisha leans forward and says, "The biomarkers from the lower unit show a metabolic cocktail that is different from the overlying horizon, but those signatures could survive low-energy events, or they could indicate a wholesale metabolism shift." She runs a thumb along a map, tracing river networks that could redistribute organics. Elena exhales and asks, "So do we believe in multiple local resets that coincidentally line up, or in one global mechanism?" Marcus answers after a long breath, "We simulate both, but the match is never exact. There are always anomalies left over that make us uncomfortable." Aisha adds, "Uncomfortable is where progress happens, Elena, but we need more precision and more independent replication." The flames crackle, a nearby owl calls, and the conversation pauses into a shared silence that is both contemplative and full of unspoken methodological planning. At the lab, the dialogue goes technical and precise, full of procedural detail and sensory texture. Tomas, the lab manager, says, "We ran the UP on 3 zircon aliquots, and the scatter is wider than expected. There is evidence of partial annealing." His hands move as if shaping grain crystals in the air, the fluorescent lab lights casting a clinical pallor. Elena replies, annealing implies a thermal event, but the sedimentology has no evidence for hot emplacement at that horizon. She slides a thin section under the microscope and points at microfractures that catch the light. Marcus leans in and asks, could hydrothermal fluids alter the system without a surface thermal imprint? Tomas shakes his head slowly. It would require pressures and temperatures that leave other signatures, and we would see that in the trace element partitioning. Aisha then offers, what if the organics were replaced or masked by a secondary influx of materials with a different chiral signature? That could explain the biomarker shift without full-scale annihilation. The conversation maps into a plan. They run through steps, list materials, check quality control. The smell of acetone briefly fills the room as Tomas cleans a pipette. The dialogue fleshes out experimental design in a way that reads like a protocol and like a narrative. Moments of tension are slowed and described with sensory detail so the stakes become palpable. One such moment occurs when a core shipment from a remote borehole arrives damaged, the crate jostled during transport. The team opens the box in the lab. The paper wrapping smells of dust and sea air, their gloves leaving pale circles on the surfaces. As they unroll the core, Elena freezes. The face of a portion of the core reveals a streak of melted material, and Marcus inhales sharply as if that one sight rearranges the problem. The lab becomes a theater, fluorescent lights buzzing, digital timers ticking. One mobile phone buzzes with a message from a faraway colleague. Aisha whispers, if that is in situ impact melt, then we have a tracer, but if it is contamination, we lose months. Tomas clamps the core in a holder. Instruments whir as they prepare to sample, each movement measured and precise. They take micro drills, sample sub-millimeter slivers, and the mass spectrometer reads values that at first seem to be random scatter and then align into a pattern that suggests transient high temperature. The team exhales collectively. There is a small cheer and immediately a sobering review session where each result is cross-checked. The tension resolves into detailed planning for independent confirmation, and the emotional arc of that moment underscores the fragile balance between discovery and error. Throughout the narrative, we insert technical process descriptions that are both precise and accessible. For example, the extraction and analysis of noble gas inclusions is carried out by sealing microsamples under vacuum, crushing them in a laser-heated line, cryogenic trapping volatiles, and finally introducing isolated gas fractions into a mass spectrometer to measure isotopic ratios. The process demands absolute cleanliness and calibration with reference gases because tiny contamination skews results significantly. Another protocol describes UP dating in zircon, explaining that grains are separated by density and magnetic susceptibility, abraded to remove altered rims, and then analyzed using thermal ionization mass spectrometer, where small amounts of element are ionized and measured as isotopic ratios that yield an age within a calculated error range. Each procedural narrative includes the sensory context, the metallic clink of tools, the warm hum of instruments, the smell of solvents, and the quiet concentration of technicians. As hypotheses and data accumulate, we introduce controlled thought experiments and simulations. A model of orbital resonance suggests that every few 100 million years, small changes in eccentricity, when coupled with mantle processes and sea level variation, produce windows of enhanced erosion and deposition bias. The simulation is described in steps: initial conditions, boundary layer parameterization, energy inputs, and output metrics. The modelers describe visualizations as color maps, animated time slices where deposition rates pulse like heartbeats. The effect of galactic plane crossings is modeled as an increased flux of cometary bodies, each with a probability of hitting the inner system. The team describes how low energy but high frequency impacts could alter atmospheric chemistry without producing a single cataclysmic layer, creating instead a period where preservation is disrupted across many marginal environments. These simulations are rendered into testable predictions, such as synchronous isotope anomalies, expected mineral assemblages, and likely locations of preserved refugia. At roughly one-third of our narrative, after presenting the central evidence and technical groundwork, we invite the audience to participate in the inquiry. If this material has already shifted how you think about Earth's past, you are not alone. The patterns we describe ask fundamental questions about continuity and discontinuity in planetary history. Which interpretive family seems more plausible to you? Natural mechanisms like glaciation and volcanism, cosmic agents such as impacts and orbital variations, or the more radical idea of replacement or intervention in the record? We want to hear your view. In a cosmic response, this response could shape a community compilation that we present in a follow-up episode, and the most thoughtful comments may be addressed by guests on the show. We read the discussion carefully because this is a community of curious minds seeking to advance how we frame evidence. Now, let us return to the laboratory and to the models that test each option. As we push further into the data, the narrative returns to specific sites where the anomalies are clearest. In a coastal unconformity exposed at low tide, the preservation is oddly selective. Shells from earlier faunas are present below the gap and different clasts above it, while in the middle there is a seam of iron-rich nodules with microcrystalline textures. In another site, in an ancient basin, a core shows successive horizons of fine-grained shale interrupted by a massive blocky interval that yields shocked quartz and microtectites. The mineral chemistry is described in detail. Rare earth element patterns normalized to chondritic values show enrichments in heavy rare earths at specific horizons, and sulfur isotope measurements indicate a rapid shift toward heavier values consistent with oxidative stress on the biosphere. The narrative connects the dots by showing how an integrated picture of lithology, mineralogy, and isotopes can point toward a sequence of events that is not easily explained by a single familiar process. Debates erupt in the literature and in conferences about the relative merits of each hypothesis. Some researchers, anchored in field geology, argue for a mosaic model where regional agents dominate but align periodically through chance and orbital synchrony. Others favor more systemic explanations, pointing to global geochemical cycles that can flip states and lead to mass reorganization. A third faction entertains the provocative possibility that some anomalies are records of technological or at least information-storing processes embedded in mineral matrices, a notion that provokes skepticism and heated dialogue. Scientific discourse in this field is characterized by rigorous peer review, replication attempts, and methodical testing, and we portray these debates with an emphasis on evidence-based critique. Interviews with senior researchers emphasize humility, younger voices push for ambitious data gathering, and funding agencies caution about speculative overreach while recognizing the potential for transformative insights. To explore the technological archive hypothesis more fully, we follow teams that attempt to decode mineral records. They apply spectral mapping, isotopic fingerprinting, and pattern recognition algorithms trained on natural samples and on known information-bearing structures. When a pattern recurs across multiple crystals beyond the expectation of natural variation, the team explores whether that pattern could arise from self-organizing chemical processes or whether it would require directed information input. This line of inquiry crosses disciplinary borders, bringing in material scientists, information theorists, and archaeologists to ask what constitutes an archive and how a natural system could mimic information density. The description of laboratory techniques here includes scanning electron microscopy, Fourier transform infrared spectroscopy, and nanoscale mapping of elemental distributions. Each technique adds a layer of evidence that is evaluated against null models and synthetic controls. The narrative emphasizes caution, science-based skepticism, and a creative openness to unexpected outcomes. The story now moves toward implications and social impact. If prehistoric time gaps reflect cyclical resets, then human history is nested within a planet that is episodically unstable, and that knowledge would influence how societies think about resilience, infrastructure, and long-range planning. If the gaps indicate an external modulation of Earth processes, then it reshapes our thinking about planetary context in the galaxy. Alternatively, if at least one horizon contains signatures that cannot be explained by known natural processes, then disciplinary boundaries blur between geology, astrobiology, and information theory. The public reaction to any of these possibilities will vary from fascination to denial, while policymakers will be tasked with translating uncertain science into actionable advice. We present scenarios in which research leads to improved hazard modeling, to the preservation of sensitive stratigraphic sites, and to international collaborations to coordinate deep-time drilling campaigns. Near the end of our investigative arc, we present 3 moments of epilogue tracing the short-term cadence of research and public engagement. 1 month after the key cores are published, several labs announce replication studies that confirm isotopic anomalies in multiple basins. Laboratories release preprints detailing methods, and a variety of teams propose new sampling campaigns. The scientific community reacts with a mix of excitement and caution. Funding bodies allocate resources for targeted shoring projects, and a consortium is formed to standardize protocols for biomarker extraction. 3 months out, the first international drilling cruise departs, equipped with sterilized coring equipment, onboard mass spectrometers, and a multidisciplinary team, including geologists, chemists, and computer modelers. Field reports come in, showing both confirmation and new puzzles, and public interest spikes as museums and educational programs create exhibits that explain what a time gap is and why it matters. 6 months after publication, the discourse has matured into structured inquiry. Several working groups publish method papers, and a public symposium convenes to discuss implications for planetary science and for heritage conservation. These 3 epilogues show a science in motion, moving from discovery to replication to institutionalization, while the larger questions remain open. We close by circling back to the emotional weight of the mystery. The planet has left us with blanks and with traces, with puzzles that force us to reconsider how continuous the story of life is and how fragile the threads of preservation can be. Some data point to forces of nature operating at scales and in combinations we are only beginning to model. Other evidence opens doors to more speculative frameworks that require extraordinary substantiation. What is clear is that these prehistoric time gaps are not mere curiosities. They are clues about the dynamics of planetary systems and about the contingencies that shape biological history. Their study demands patience, rigorous methods, cross-discipline collaboration, and an ethical commitment to transparency and open data. If narratives like this inspire you to keep thinking and to participate in evidence-based debate, please subscribe and join a community of curious minds. We aim to bring rigorous investigation to the most challenging questions and to share updates as new data arrives. Thank you for listening and for being part of the conversation as we try to recover what was lost and to understand what those losses tell us about our past and our future.